All right, now let's get started. So today is actually a bit of a lighter lesson. What you see on the screen is the result of last lesson. So we have this widget thing with the default constructor, with the any operator, which is the most important operator with widgets. The widget is a monad, but in our case we only have the map function, so we only implemented the functor part of it, because join is actually quite irrelevant. It's more about the sort of horizontal composition of multiple widgets next to each other of any. That's much more important than the idea of nesting and flattening widgets, which doesn't really happen that much in practice. Also, I brought a little bit of things that I have already implemented. So for example, the definition of the function, the definition of the updater, the definition of sum, for example, which is either left or right, etc. Because I wanted to bring an implementation of coroutines that I actually use in practice, which is very similar to the one we have. You can see context, state, result. The definition of coroutine I brought also has this idea of events that you can consume with on. So you have an event handler coroutine, which is very nice. We can ignore it for all practical purposes, or you can study it on your own. But I've taken this because it's a standard implementation for which I already have my bridge. What bridge, I imagine you might be asking. So the coroutine is a monad, and what the coroutine does is it produces results. But when does a coroutine produce a result? We don't know, because unlike the state monad, the coroutine monad has a lot of ways to, well, suspend forever, keep waiting forever, and in general not produce a result. Of course, also the state monad could have an instance of infinite recursion, but in the coroutine this might even be intentional, that the coroutine never actually triggers with a result. And this is very similar to the widget, actually. The widget also has this timing component, because when does the widget, which is actually implemented with something that takes as input a callback and returns something renderable, a JSX element, which might call on output? Never, so 0 times, just once, many times, but with big intervals of time between one call and the next, and so on. So in this sense, the widget and the coroutine are quite free in the way they call they trigger output. Now, when you have monads that are similar in the way they perform their data flow, it becomes possible to define a translation. And this is what we're going to see and study today. So, what we're going to do is we're going to define a way to embed a coroutine that operates on a given state into a widget that operates on that same state. But be careful, because I'm mentioning state, not the actual output. Our widgets, if you remember, they always produce an updater of something. And in our case, the top level, our actual state in our case, is this per programmers. So where we have these 2-person instances, programmer 1 and programmer 2. This will be our state. And we will define a coroutine that can operate on this state. The slight mismatch is that coroutines have 2 ways of propagating changes. One is in the form of a new state, one is in the form of a result. The result we will ignore. So in this sense, we're not saying that we have a coroutine where the result gets mapped to the O parameter of the widget, which would be actually quite natural. But what we will do is we will map the state of the coroutine to the O of the widget. So it's not a direct translation of the coroutine as a monad in result and the widget as a monad in O. but we're free to do whatever we want. Okay, now let's go to this this bridge file. Yeah, okay, the name is terrible, so coroutine to widget is perhaps a much better name. I'm also going to clean up things a little bit because I don't want to be a monster here. Let's clean things up a little bit. Also, we have multiple definitions of updater, so it's all pretty dangerous stuff to leave duplicated. So let's move this definition first to a file. Let's continue with cleaning things up a little bit. So I'm going to move everything, the widget stuff, to the widget file. Okay. Then I'm also going to start removing things. I also don't want to carry. I don't want to carry things around that we otherwise already have. Replace with. We also have in our core definition. Why is widget unhappy? Let's take a look. Oh, missing a comma and missing the comma. Yes. Let's see. Okay, now we are. Looks like we're happy actually. Okay, so what happened? Well, because the widget was based on a definition of fun, and the coroutine was based on another definition of fun, I made sure that they use the same definition of fun and even the same definition of updater. This can save us from quite some headaches. Okay, so we will define a coroutine component, and it has properties. Okay, this coroutine component is an old school class component in React. Modern React does a lot with function components. Be careful, function components, if they use state, are not functional, because functional means that they don't have side effects, but they are function components. Function components are a bit limited. What we need for implementing our coroutine embedding is a more fine-grained control over the life cycle of the component. So we're going to use a class, which is objectively uglier, but yeah, such is life. Okay, the coroutine component needs to know the context of the coroutine and the state, and it takes as input, well, the current context, which is going to change all the time. So this is going to be re-embedded every time, so that the coroutine can trigger on the new state. Then we get set state. What is a set state? Well, set state will be a function. We have this basic fun construct. I will show it very quickly. Basic fun is just a normal lambda, whereas fun is the one with the then operator. So when we take a parameter from outside, we get a basic fun, but we try to convert them to fun as quickly as possible because we like the then operator. So basic fun doesn't require anything to the caller. It's a basic fun that we are given from outside. It takes as input a basic updater over state and returns just void. So this we can call whenever we want to actuate a change in state. And where do these changes in state come from? They come from a coroutine. Which coroutine? Well, I will call it initial coroutine that we want to execute. And this will be a coroutine of context, state. The events for now I will leave to undefined, and the coroutine will return never because we don't really care about what the coroutine returns. Sorry. And the result will be unit. Yes, okay. Now, the coroutine itself needs a state. And the state, you know, I like to copy stuff around and declare myself lazy, and that is the case. Well, I mean, the context is passed as a property, the set state is also passed as a property, but the current coroutine, so how far are we? Well, this needs to be passed, of course. Or this needs to be tracked. Okay. If we go back to the implementation of coroutine that we built on the command line, well, we knew that we needed indeed to trace the current coroutine. and we had a way to modify the state. So this is a sort of more abstract interface to define that. Funnily enough, even though these types are defined for a React implementation, so far they have nothing to do with React, and this is sort of the fundamental interface that you would need in order to have something that is capable of running a coroutine. This is the state you need to track. This is the input you get from the outside context. Now we actually get started. So the coroutine component, or coroutine widget actually is a better name. No, because this is not a widget yet. No. The coroutine component, because, pardon, the widget will be the widget that wraps this component. But the component itself is a component, yes. Is of course generic in context and state, extends React dot component of, okay, well, the component has the coroutine component props of context and state as the properties it gets as read-only properties, and of course has a coroutine state as the state it runs. And now we can actually proceed with the implementation. The constructor takes as input properties which have the type we declared. In the constructor, we call the constructor of the base class so that the React.component class can be initialized. Very good. It's kind of ugly. It's really ugly, actually, not kind of ugly when compared with function components. But again, so much more powerful. But here, finally, we can say, okay, the state gets initialized by putting in the current coroutine props.initial coroutine. Why do we need to distinguish this? Well, because the implementation I'm going to define actually starts all over. So the coroutine, whenever it terminates, we restart it again from scratch. All right. Now we track an internal variable running, which is set to false. This internal variable is not part of the state because we want to be able to update it faster than updating the state, and we absolutely do not want to cause any re-renders, any component it update, any component lifecycle. It's just an internal, let's say, housekeeping variable. Also, we will need to track the, need something to track the loop, but that is for later. Let's define the render function, which will do absolutely nothing. So this is not a component that renders anything, but the, let's say, actual payload of running this thing will be three things. Should component update, which takes as input a bunch of parameters and determines whether or not the component should update based on the value of the new properties that came in, the old properties, etc. And here we will see, well, this component should never be updated. So from the perspective of React, we're telling React, whenever you think you wonder if you should update this component, re-render it, remount it, etc., answer is no. Do please absolutely not, because we don't want React to interfere with our rendering cycle. When the component is about to amount, because we are legitimately removing it from the DOM, it is still a component that we're putting on the screen. So when we actually remove it, okay, then we have to stop. We have to stop the loop. So we say that running is false, and also we will track an animation ID. I think it's going to be a number, but I'm about to be proven wrong. And when the component has to amount, we call clear interval, because we will run the loop in an interval and we pass this .animation ID. Okay, I'm happy to see that this actually worked. And the most important of all, when the component is mounted for the first time on the DOM, on the screen, then, okay, running is going to be true, because, well, we start running, and we run until we unmount. So the coroutine just keeps running forever. Well, until, no, not even until it terminates, actually, because it will start again. We save the timestamp. Last timestamp, yes. And this will be date.now, because we need delta t. So we need to actually measure how how much time actually elapsed between now and the previous call, because if the machine is being a bit slow, then the last timestamp might be bigger than the interval we requested. Now we define a tick function, which is going to do all the updates. This we're going to write in a moment. And then finally we can say that the animation ID is set interval of tick, which will be called every, let's say, 50 milliseconds. So actually every 50 milliseconds. Because this thing is going to do a set state whenever the coroutine wants to perform a set state, and this would cause a remounting, etc. That's why should component update is very strict and says no, because, well, this set interval is more than enough, and we don't want to have any interferences from React's life cycle. So we have this sort of infinite loop on one side, we have React doing its little update cycle, and we want to keep this as separate as possible. And now for the actual implementation. Okay, so, well, first thing we check if we're not running, then we should return. So we really don't want to do anything. Also, as a good measure, I'm also going to re-clear the interval. This can't really do much damage. So make sure that if for whatever reason someone puts this.running to false, we don't want to continue running this loop. Okay. Otherwise, okay, now we can actually tick the coroutine. How do we tick the coroutine? Well, the coroutine we get from the state. And we take the current coroutine and we can just run it. And now the coroutine expects the context, the delta time, and the events. Now, the context we can provide because it comes from the properties, current context. The delta time, okay, the delta time we need to get. So, current timestamp will be date.now. Delta t will be the current timestamp minus the last timestamp. And of course, the last timestamp needs to be updated to the current timestamp, but only after having saved the delta t. Okay, the events, well, for now we're ignoring the events. That is, let's say, homework for you, in case you were interested. Okay, now, the next step, or the step, will be the result of this coroutine. And now the step is a coroutine step. This you have seen already in the past. Now we check. What do we have in the step? Oh, no, because I have an implementation that does this for me. So what we can do is even better. We can actually invoke, because we have coroutine of context. Wait. So I have this coroutine here. And this actually has a tick function that is going to take care of this thing for us. So we can pass it the context, we can pass it the delta t, and we can pass it the events. And we can pass it the coroutine. I was about to rebuild this whole thing, so no reason not to do it. And the generic argument goes, wait a second. The coroutine object. Let's take a look at what arguments does it take. It takes no arguments. Okay, very good. So tick is generic in context, state, events, and result. Good. And are we missing the delta t? Oh, it is the last argument. Very good. Okay, so what coroutine.tick gives us, I'm still going to call it step, but it's a sort of shorter version of the coroutine step, because it can only be done or continuing. So if we're done, If we're done, then we'll have to set the state to store in the state that we're starting all over again. So I set the state, and in the state here, let's turn this into a lambda. I make a copy of the state. Should there be anything else, and the current coroutine will come back from the initial coroutine. So we start all over. The second argument that we can pass to set state is what we do after set state has terminated. And in this case, if step.state is not undefined, then we are actually, the coroutine requested as its last operation to actually perform a state updater. So we invoke this .props.setState with step.state. So we honor the request to run the set state. If the coroutine is not done, on the other hand, well, what we're going to do is quite similar, because we are going to set the state, because the current coroutine becomes step.next, which simply says what we're supposed to do. What we're supposed to do next, what is the rest of the coroutine. And of course, if not only we get next, but also a new state, which is not undefined, we perform that change in state. And that seems to be kind of it. Well, we haven't built the bridge yet. This is the first part of the bridge. So with this implementation, unless there are any bugs which we're going to test for now, has bridged the gap between coroutines and React. So we can actually run a coroutine in React. Let's go back to our index index.tsx. I will define, I wanted to show you before we continue, I wanted to show you how tick works. Tick is actually pretty simple, because we get the coroutine and we run the coroutine, and then we check the step, and depending on the step, you know, because basically if we get yield or waiting, etc., then a yield which is the same as suspend, waiting which is, well, the same as the waiting we built, then we squash all of these into a result of type continuing, whereas if we got the result, we give kind done. So this simplifies a little bit consuming a coroutine, because you only have to check for two things, done and continuing, even though behind continuing a lot of complexity is hiding. So the whole logic of the coroutine is what to put into the next step in case of a continuation, in case of continuing. Okay. So that is a very useful aspect of making use of coroutines in practice. Okay, so now that we have these pair programmers, I actually want to add the age to the person, because numbers are easier to work with. So age is an updater of number, updater of person, name, and person.age and person.age. Updates to the numbers are very useful in coroutines, because they allow us to see just values incrementing, decrementing, etc. And they are a little bit more intuitive, in my opinion, for this kind of test scenario than updates to, for example, the name and the surname. Okay, so the coroutine that we're going to work with is going to be, well, I'm going to define this co, which is a shorthand of the co-typed factory, which takes as input the context, which is everything we can read, the pair programmers, the state, which is also the pair programmers, we can both read and write from the pair programmers, and no events. And co is super useful, because now in co we have, let me call this, because in co we have all the operators like any, await, get, state, repeat, blah blah blah, but with better type inference, because we have already specified the type parameters for the context, the state, and the events. This is a very neat trick, because then you simply write code.sec, code.wait, code.this, etc., instead of having to write coroutine .wait, for example, which needs to specify the context, the state, and the events every time. Whereas if we simply say code.wait, while code.weight is not generic because we have already specified the type arguments here. So code typed factories is no more and no less than a cache of the type arguments. Simple pattern, but also quite powerful. Okay, let's define our test coroutine. And what will our test coroutine do? I guess what it is going to do is it's going to increment the age once of the first programmer, for example, like something that is a little bit sequential. So set the state with, okay, we want a state updater of per programmers. So we can say per programmers dot updaters dot programmer one. And what do we do to programmer one? Well, we take a person updater of age and we increment it. We don't have increment, it's okay. Underscore goes into underscore plus one. Why is it unhappy? Oh, let's get a basic updater. This is actually a better pattern. Like when we have an argument, I'd rather get the basic updater, which is just the dumb one, like a normal lambda. But what we get as a result is an updater, because what we want to get is something that can be chained. So basically, what we accept as input doesn't need to be chained, because we just need to call it. So we can just pass a lambda here, which is, in my opinion, actually pretty neat. But the result of this updater has then, because we immediately wrap it into an updater. So here I could have something else, like a person. Person dot updaters dot name, and here I could even say replace with Johnny. And well, obviously here we don't provide something with a then, because this is just a lambda, but the lambda gets wrapped in an updater, which then has a then. If you ask me, this is very handy, and also quite cute and very logical. Okay, anyway, so we increase the age of programmer one, and we wait for about 2 seconds, and then, okay, let's say 500 milliseconds, because I actually want to see stuff happening. Then we update the age, but we increase it by 2 of programmer 2. Okay, so this would be an example of something that is very sequential. Okay, now, oh yes, of course, we're missing the age from the initial values. Well, let's start with, well, they're not really programmers yet, but we might as well start them early, right? Programming is still a very useful thing. And inside, well, we have this set state. You know what? For now, we're going to run our coroutine component next to hello world. This doesn't really render anything, so it doesn't matter much. Okay, so we have our coroutine component. So wondering if I'm instantiating it. No, it's probably not exported. Yeah, so good luck with that, I guess. Coroutine component. The initial coroutine will be, what did we call it? Well, age increase background process. Ha! Let's give it a proper corporate name. Very good. Might be that we need that the type parameters are an issue. So I don't know. I'm trying to see how far we come. We have the initial coroutine. We also need to provide, well, the current context and set state. So set state will just be set state. The signature is correct, and then the current context will be just a state. It's unhappy. And oh yes, let's see. Okay, did it guess the type correctly? Yes, so it knows it's a coroutine of pair programmers. Set state pair programmers. It looks like it's happy. It looks like it understands what is supposed to happen. Okay, let's run this thing. I mean, can you see this? It's working. I mean, come on. Well, I get so happy for these things. Oh my god, what a nerd. But look, I mean, we have something that's based on timing, like, and this is exactly what is missing from React. And what is missing from React, React has this beautiful thing where you can compose the way things render, but the problem about rendering is that everything is sort of active all the time. So React is not really suited, not well suited at least, for doing things that are sequential and asynchronous in nature. So do something, wait, etc. But here, yeah, whatever. We can do whatever we want. Okay. Of course, you might already have guessed that, well, embedding this thing into an actual coroutine is pretty easy. Into a widget, because yeah, we just need to call this coroutine component in a widget constructor. So we just wait, where is it? So we need something that can be rendered. Here we're calling widget.any, but in our case we will need widget.default. Okay. And we will then call it in the any of pair programmers. Yes, very good. So the age increaser widget will be widget.default. Now here we get, well, on output, which is, guess what, set state. Let me give a type for this. So we want an updater of pair programmers. Well, and actually we also want the current state. So we're going to get both. So we get the current state as input, and then the widget itself produces the updater that is going to be fed into set state. We have widget.default with set state. Okay, very good. Here we can call the coroutine component, which we actually don't need to call anymore here. The current context are just yeah, the pair programmers. It's not even set state. Okay. It is very angry at us. Why is it so angry at us? Let's take a look at what. Oh, an error is missing. Oh, so terrible. Okay, we're getting closer. Let me see if I can. It doesn't know the type yet. Okay, so let's make it clear that this one is a widget of updater of pair programmers. Okay. Because in the widget we are expecting a full updater, but actually this is probably too restrictive. So or the widget itself can also just return a basic updater. Let's see if this is enough. Yes, this is enough. Yeah, okay. Because what we pass to set state is actually going to be an updater, but then set state doesn't care about it being an update, an actual updater with them, because the widget just needs to pass it back up. I guess no, this is no, because we want to compose it. No. So we're going to fix it. Okay, so if set state gets as input an updater, but this set state here gets a basic updater, what we're going to do is we get the basic updater underscore, and then we pass it to set state, but we just wrap it into an updater. Yes, okay. Easy. Not really, but anyway. And now we can simply put this into any. So we can pass the age increaser, we pass pair programmers, and that's it, because any will take care of processing the output, and whenever this age increaser wants to invoke set state, well, set state has been passed and is going to be passed implicitly. And it still works. There you go. You can tweak it, of course, you can play as much as you want. We can run things indeed in parallel. We have code.any, we have repeat. We can indeed do whatever we want. So we could do also, yeah, there's a while statement. This is actually fun to play with, to be honest. The thing I'm not going to show, because I believe that it's hopefully clear enough, is that this age increaser, this pattern here, you can easily generalize it. Like you could say that this is the state, this is the updater of state, so the state can also become generic, and then you just call the coroutine component with these values, and as an extra parameter that you would probably pass as an input to age increaser is whichever initial coroutine do you have, and it needs to have the right types. So I hope that by now you can see how easy this would be to generalize. I can at least give you a hint. So coroutine runner, and we would say, yeah, this is generic in the state, and then this would be the state, and this would be the state type, and this would be a widget of updater of state, blah blah blah, and the rest actually really flows. Of course, yeah, we also need the initial coroutine as input, so we would get it. As an extra parameter. This is actually so trivial that I will dare say I leave it to you as homework. The big deal of this is that by seeing that if we take the two tips of the iceberg of our course so far, which are the coroutines in order to manage the domain of concurrency, and the widgets in order to manage the domain of rendering. And these things have composition, have the any operator, which is perhaps the most useful kind of composition operator, because it's really I have two things and they have their life cycles and I want to somehow merge them together. So it comes back almost everywhere, any. And we have these two domains and they solve two big problems. And the question is, well, if I can take monads and convert them one to another, and this is not always possible, by the way, but in general, it is something that can be possible, and when it is possible, it is very powerful because it allows us to add one monad into the other one, which is more expressive. And in our case, the widget monad is more expressive because it actually can genuinely do more than the coroutine monad, because the widget monad has the rendering plus this sort of concurrency, plus a widget can produce multiple set states, etc. Whereas the coroutine is a little bit more linear and it has no rendering. So we can embed the coroutine, which is super powerful, but less than the widget, and we can embed it in the widget. And the advantage is that we can have a bit of our program which has nothing to do with rendering, but only with state updates. So this doesn't require all the power of the renderer of the widget. Also, word to the wise, this doesn't use React in any way. This is just the business logic of our underlying timed processes of our application. So it's also nice to have something that doesn't depend on a framework. This is just normal TypeScript code, which we isolate from the rendering part, and then we embed it into the rendering part. And this embedding is super clean because we have our translation layer. The same logic can be done, for example, when embedding something like promise, which is even more limited than coroutine, inside coroutine. And we actually have it already. I'm going to put this in the repository, so you get a promise, and you can turn the promise into a coroutine. So you have a promise that gives us a result, and we get a coroutine that returns, well, either a result or an error. So this is another form of embedding. The beauty of this is, if I have a promise, I could say, well, convert the promise to a coroutine with await, and then convert the coroutine into something renderable with our coroutine to widget. And so you have achieved the ability to also translate a promise to a widget, so to run asynchronous code inside widgets. But because coroutines are a lot more powerful than just promises, you could have a wait inside a while loop to define your own retry loop, which is something that is actually very, very difficult to do in React. And there are all sorts of libraries and they all do this very poorly. And not only can you do it, but you have full control while doing it. I do honestly think this is a very powerful and expressive conclusion of this course that started from very theoretical and ended up in a place that is extremely applied, because I mean, we're talking about promises and rendering in React, and you can imagine, well, this could also be done with Angular, it could also be done with Vue, and we looked at coroutines, and also we kept the coroutines isolated from React, but you can imagine that this sort of translation, this coroutine runner that we built, could have also been done if we had a sort of widget library for Vue, which would probably have a constructor, that takes as input something with an updater anyway, because we're kind of required, and then we could have bridged the promises to coroutines to Vue widgets, for example. One of the unintended side effects of working like this is that there is a lot of code that has very little to do. For example, this bit here, this bit here, this bit here, this bit here. This code has very little to do with the underlying framework that we're working with. So we keep a neater abstraction between the tools and technologies that we use, and technologies change all the time, from the foundational elements that are constant. And this makes it possible to actually write smaller, simpler code without having everything mixed together. And a lot of people will watch you program like this and wonder whether or not you have all of a sudden acquired superpower, or if you're a very big-brained developer. But the truth is, by removing the things that are unnecessary, because they are universal in a sense, and splitting things as away as possible from technology, then you are much freer to work with the real-life technologies such as React and Webpack and RSpec and all these beautiful things, and to focus on those complexities without being overburdened by the complexity of everything else on top of it. And this makes you a much better user of technology, and especially a master of computing. Thank you again for being here once more and sharing this part of the journey. I think I've used the word beautiful more than I ever have in any other course in my life. And life can feel stressful and dreary, and knowing that it can be beautiful, especially in your job as a programmer, I think is something that you owe to yourselves to never forget. The fact that programming is meant to be beautiful, is meant to be amazing, and is meant to be incredible. An incredible tool to explore and understand the world better. It is not easy, but it is such an exceptional privilege to be able to experience the world like this, that I wish you with my whole heart that you will manage to do it. And not only just do it like I've shown you, but actually find out ways to do it even better.